people. The minute you tell them they have to compile code, you lose another half. So in this case, you don't have to compile anything, and you don't have to. It's all GUI driven. But there are terminal-based sort of background if you wanted to do that. If you wanted to play with the code, you can also get it off either GitHub, or I have a Git instance running as well. So that should be easy enough to do. And if you wanted to use this on some other kind of operating system, it is, the code's there. You can't compile the C++ code, but you shouldn't have to. Compared to some of the other codes, I think a lot of it's really is focused on signal processing, and we'll go through that with the demonstration here. I think there's a fair number of options, and it's a little bit, I don't know, maybe you can play with it more than other codes. I'm not sure. I'll let you guys decide that. But it has signal processing. Right now, it can only import the GMR and MRS MIDI data. I would like to add iris data as well. There's noise removal through both reference loops and also harmonic noise cancellation. And I don't have spectral windowing yet. That'd be a nice addition too. If anyone feels like they'd like to contribute, it'd be great to have. The kernel generation, it uses an electromagnetics library that I wrote as well, written in C++, and I have compared this kernel to the MRS MATLAB kernel, and they're in very good agreement. And all the kernel calculations are done on, it's called an adaptive Octry grid. So you can see that on the right here, where basically the kernel sensitivity can get very fine details near the loop, and then away from the loop, the resolution of the mesh naturally decreases, and it's a fairly computationally efficient way of doing that. And it's quite flexible as well. Inversion is quite simple right now, just a Qt style inversion that's available. The regularization is selected through an L curve, as shown here. Again, there are other options. I know lots of you guys are proponents of other approaches, but this is a simple approach that seems to work well. You can select water content, things like that as well. It's also pretty flexible. You can do arbitrary transmitters. So on the left here is a survey that I did where we had 3 different transmitters that were slightly overlapping, and each of them are also receivers. So you can invert multiple receivers at once and have more than one transmitter at once as well. So that's fairly flexible. I don't know if you can do a lot of things with that. It also can have grounded sources or grounded receivers as well. It's shown on the right here. That's an electric field from a grounded receiver. But you could. Aaron Davis a while ago had a grounded receiver paper that he published, and I processed it with Akvo, and it worked well. And another thing too, it's reproducible. So as we're going through this, you can see that all the processing steps are recorded in the final data file, as shown here, which is nice. So then when you go to publish a data set, or even if you go back and look at what you did, you can see all your processing steps. And so you remember like, oh, this is, exactly what happened with this data set. So that if you give that raw data to someone else, they can reproduce your findings. And so thought we'd kind of jump into the code here a little bit. Yeah, if you wanted to go ahead and follow along, you can go to the website here. It's hosted on pypi.org, the software. That's how you do pip install. And we have this tutorial here, and it's not the current fast times issue, it's actually an older one. So I'll just go ahead and jump into that then. Are there any questions? Please feel free to interrupt like you did earlier. I'll close this window.
Trevor, yes, just to tell you that it's clear and we are following. You're not alone.
Okay. Okay. Can you still see my screen then?
Yes.
Okay, great. Okay. So again, to install, all you have to do is to type pip install Akvo. But here I will just fire up the GUI. And the data set I'm going to be working with here is an older GMR data set from about 10 years ago that was collected in Nebraska, that's been published several times by, when Rosemary Knight was doing a lot of NMR, this is one of the data sets that she was working with quite a bit. So the GUI opens up here, and there's 3 different workflows. So workflow 1 is pre-processing, which is all your signal analysis, modeling, and then an inversion workflow. So we'll start off with the pre-processing. And if you want to import the data, you can just go to File to Import, and you can import the GMR data, media data. I'd like to add iris data as well. Just haven't gotten around to it. So we can open a GMR data set, and this is the GMR header. You can click on this, and this data set has stacks from 2 through 19. You can do that. And the way that, or it's 2 through 18, you can specify the stacks you want, and it's a Python way of doing it. So you have to say 2 through, and it doesn't include the very last indice. But if you can see it, when you hover your mouse over different things, it tells you kind of, hey, this is what's going on. So, so that's there. Data channels here, you can select the data channels you're using. And then you can select your dead time and your reference channels. In this case, we have 2 and 3 are reference channels. I'm not going to import all of them right now, but you can import these data sets, and it goes and reads the file. And you can see sort of the raw data that you're working with here. And after it imports, you can go ahead and look through, and we see a lot of harmonic noise in this data set, which, so this is a good data set to sort of play with some of the signal processing. I'm going to close this and reopen. So since the import takes a little bit of time, you can go to File, Open Akvo Preprocessed Data Set, and here is the full data set that's loaded. So at any point, you can process the data, you can go up to File, and you can save where you're at and come back to where you were. The next step, you can do these in any order, but sort of as a natural progression is to downsample. And the plotting takes quite a bit of time. So, if you don't want to play with that data, you can click the plot, and here it's going to downsample the data because the GMR data is quite a bit oversampled. This functions as an anti-alias filter as well. And then the filtering, if you want to do any pre-filtering, since there's so much 60 hertz noise, this was collected in Nebraska, so yeah, 60 hertz, not 50 hertz. You can do that in this window as well. You can do a frequency domain window, and it tells you how much dead time will be incurred using this. And so this is a 600 hertz Hamming filter. And so you can go ahead and apply that. If you're going to also apply, the next step below here is a time domain bandpass filter. And if you're going to use a cascade of filters, you may not want to trim that dead time because if you're careful with how you do that, you don't need to do it on both. So that's just a simple frequency domain windowing. And then you can design a bandpass filter as well. So here's just a Butterworth filter, basically about a 300 hertz Butterworth filter. And it's 0 phase. It actually does it forward and backwards. So you can apply that as well. So at this point, you've now imported the data, done some simple filtering. And then if you wanted to see what we're dealing with here, you could go ahead and stack this data. And you see that we have, the bottom is the full spectrum here. And the top would be a stack of all the data sets. So it's still quite noisy. So that's, needs some noise reduction. So I'm actually going to start back here. And so here's a data set I saved that has that same windowing and bandpass filter. So in noise removal, you can go ahead and do harmonics based. And this has the ability to do 2 different harmonics in your, or 2 different frequencies. So in case you have multiple sources, and you can set the base frequency, so it'll search around either 60 hertz, or you can adjust that to whatever. And you can do segments, so you can say, okay, I want you to split each time record into 2 or 3 segments in case things are changing quite rapidly. And then there's a few options for sort of how it does its searching. And you can, again, plot this. For a lot of the US data sets, and I've talked to a few people about this, I haven't found that the harmonic modeling does particularly well. And you can also do it, of course, before you've done the filtering. You can see here that we have some reduction in our noise here at this point, but it's in this particular data set, it didn't have a whole lot to offer, but it is there. There are some data sets that I've worked with that it's been really nice for. I don't know if the US just has a more ratty electrical grid or what, but I just have not had as good a success, I would say, as maybe on some of the US collected data sets as I know that you guys all have. So open up that same data set. Instead, had very good luck with reference kind of noise reduction or noise cancellation. And the approach that we've taken here, we have a static time domain filter that you can do, but I prefer frequency domain filter you can do. I prefer a recursive least squares time domain approach instead, where you have filter taps, a forgetting factor, and you can do this with multiple reference channels. And you can also apply a principal component analysis prior to doing the noise cancellation. But this is shown to be just quite a bit more effective, at least on this particular data set. So you can go through time here and you can see that it's, really reducing that noise substantially in this particular data set. So it's very effective. This does take a little bit of time too to go through all of it. So I'll go ahead and zoom us forward. Are there any questions? Okay, so we've loaded our data, we've done noise removal. Now we can stack this data set. So we can calculate our, and this information down here is just the header information, tells you what transmit frequency you had, the number of pulse moments. This is a lot of pulse moments. It was, not time for that right now. 40 milliseconds FID pulse. And so we can calculate our pulse moments here. And we see that in this case, the way the GMR works, it loads them. It does several different sequences of pulse calculation, and then you can stack the data too. And if you remember the previous stack, this is a vast improvement over that. So that noise cancellation is working pretty well, as you can see here. Again, I haven't done any sort of the spectral windowing approach. I just have a quadrature detection right now. There are some options here for different ways of doing this. You can have a dog box or Levenberg Marquette. They're just different ways of sort of selecting basically that nonlinear optimization, the approach it's taking to fit this. You can then plot the quadrature detected data. This is the real and imaginary version of it, amplitude and phase. And all these plots here on the left, this is just a matplotlib library. You can go ahead and zoom in and sort of interact with the data, which, and so you can kind of see what's going on. And then I do a gate integration as well for data reduction. And you can specify the gates per decade. I found 20 is a fairly good sort of working number to do. This takes a little bit longer than you might think, because while it's doing this gate or this time gating, it's taking the phase data and looking at the residual of that phasing to use that as sort of a noise instance, and using that noise instance to help characterize the noise level of the data set. And it's doing that through a statistical bootstrapping technique that does take a little bit of time. And some of these methods could be parallelized. A few of them are parallelized. This one isn't. Okay, so that's done. So now you can plot up this gate or the window data. Again, you can do real and imaginary plots, amplitude and phase, and then your phase data, where we show the corrected amplitude data on the top, and then basically an estimate of the noise here on the bottom. And so we're getting about 22 or so nanoteslas of noise in this data set. So at this point here, now we have the data fully processed. This might be ready to invert. You can start adding information, and this will all again be added to the data set itself. So you can say, in this meta tab up here, you can say where you're at. So you're in Nebraska, site 58. You can enter coordinates. So if you have, want to put GPS coordinates in, you can do that here with your UTM bands. You can put the date of the survey in here. So it's the time and temperature. You can include magnetic field inclination and declination, of course. In this case, the field inclination was about 69 degrees, and the loops were aligned with that. So it's an effective declination of 0. And then this is the background intensity, magnetic field intensity. And you can adjust this up or down for a transmitter offset in the case of off resonance pulses. In this case, we're pretty darn close to being on resonance. So the next step is adding transmittal loops. So you can say channel 1 in this case. And the loops themselves can be whatever. You can have circular loops or polygon. A polygon can have any number of different nodes on it. In this case, it was a square. But we're going to add a channel 1 transmitter and receiver. And you just enter the coordinates for that. So in this case, it was a 100-meter loop. And so you have to enter the corners. And I did add a small, 1 millimeter negative height to this because the wire does have sheathing around it, but it also stabilizes the electromagnetic calculation a little bit. So you can specify the number of turns you want. And so now we have that. You can also add field notes, if you want to say, anything about the survey. Whatever that might be. And so all of these get saved in, this will be in the data header. So now that, we've done all of our processing, we can see that, we imported this particular file name, what day you opened it, the type of pulse, data channels, reference channels, then this metadata. So where you are, the coordinates, date and time, those things, and then all the processing steps that got us here. And so at this point, you could then save this. So you go File, you can export. It says Export to Lemma, but that's just the next step for like inverting this. And we can say, demo. And so that's sort of the full data processing. And a lot of those steps, of course, can be altered and changed. I don't know how I'm doing on time, if we need to move on here or not. For modeling, if you want to add a resistivity model, so now that we've done that, we can then work on adding a resistivity model. I have to recall what the resistivity model was. It was basically, I think, about 20 meters of 20 ohms, 20 ohm meters, and then maybe it's like 30 ohm meters below that. It was quite conductive. So you add your resistivity structure here too. This is for kernel calculation. And then you just select a data set that you want to align with. So we just, saved this. And then for the kernel calculation, you say, okay, what is my transmitter? And we only had one loop here, but if there were multiple loops, you could select one or more than one transmittal loop to specify as the transmitter. And then receivers as well. You can have one or more than one, which in that case would look at basically a stacked data set or a summed data set. The kernel calculation is done down here. So we know that our loop, we specified that the loop was starting at some coordinate 0, going out to 100. So we want to have our origin a little ways from that. So we'll go to negative 100. And so this is going to integrate the MRS kernel over a 200-meter cube that starts at some point negative 100, negative 100. We know that our loops are in the center of that. And again, this is done on that Octry grid. You can specify the number of layers you want in your kernel. 50 is quite a bit. And then these will get larger with depth. You can do geometric or linear or log spacing on that. Thickness of the last layer, thickness of the first layer. And you can then calculate your kernel. And that will call up an external process. And so the kernel calculation is parallelized and goes through fairly quickly then, calculating these values. It does report back a little bit here. And the shallower layers take a little bit longer than the deeper layers. So, depending on how exact you want to get this quadrature or this Octry, you can tell it basically how good of a solution you want. So you can say, I want this minimum level is, make sure you split the Octry into at least 8 different sub blocks. And then the maximum level is only refine down to a certain level here. This was pretty quickly done. And so we could refine this with, by increasing this min level here a little bit and this branch tolerance. So basically this says, hey, I'm going to get a kernel that's, for every different split is 1 nanotesla, sort of my point at which I'm going to let that drive it. Zoom has taken over my computer here. Okay.
By the way, Trevor,
Yes.
How would you qualify the computer you are using? Is this a very strong computer or with
This is just a little laptop. So it's a 5-year-old 8th generation Core i7. So yeah, nothing too fancy.
and memory necessary 8 or 16 giga?
16 gigabytes of memory. So then, so we did that kernel calculation. So then once that's done, you can go ahead and do an inversion. And so you go ahead and you select your data set again. So that was, this was the data set that we just saved here. And you select the kernel that you want to use. And this workshop TAL was done with a little bit higher resolution, took maybe 10 minutes instead. And then you can invert whichever channel you want. In this case, we only have one channel, so I'm going to invert channel 1. and you can specify which model objective function you want to use. In this case, we're going to just do a smallest model, but you can do smoothest. And so basically that's just whether or not you want, it's sort of the roughness, right, that you use. It's a fairly standard Tikhonov style inversion. And you can specify this model objective function both in depth and in TT space. And then you can calculate a DOI as well. So all you have to do is, click invert, big red invert button, and it will run here. The inversion does take a little bit longer. So I'm going to go ahead and stop this in just a second here, and I can show you the results from that. But it just calls the C++ code from the background and runs through this. So, and it probably may take like 10 minutes to complete. So I won't make us all sit and watch that. So once that's run, you can look at the inversion results. And so this is the result of the inversion. Let's see here. Where you can see, just the recovered water model with both depth and then T2 star. And as far as pulse moments here, right now I only support FID pulse moments. I would like to add some of the other, exciting new pulse moments as well. Let's see. And then this is the resolution matrix that was calculated. And the resolution matrix is calculated using a sort of a point spread function. So basically what I do is take the final regularization level and then run back through the inversion engine little single delta models at each depth layer to see what that point spread function is actually running through the mechanics of the inversion. And so here's basically an example of that. This is that point spread function as we're inverting small little blocks of water at different depth locations. It's a similar approach to the truncated SVD, but done at the through the exact inversion engine that was used for the inversion. But that seems to be giving a pretty good depth of investigation. And then you can look at, there are several PDF files that get generated. So you can look at any of them. And this is our data space plot. So this is the observed data, the predicted data, and then the misfit. And so we see, a pretty good data fit with this older data set here. So, I think that my hope is that this is a code that, is easy enough that pretty much anyone could use without a ton of sort of background in the method. Hopefully we talked about trying to encourage new people to take up this method. So hopefully it has some value for people. And I'd be happy to talk about any of this, but also know we need to move on too. So again, you can follow any of this. That Fast Times article really walks you through all the processing in a lot more detail, and the data is up there if you wanted to play with it.